Hi, I'm AJ Laschober, and I'm a senior at Wilsonville High School. As many of you know, I enjoy being active and I enjoy playing sports. During my time in high school, I have played basketball, I have played soccer, and I run track. When I'm not playing sports, I like hanging with my friends and just being active in general. Next year, however, I am going to OSU, where I hope to get a degree in mechanical engineering. So today we are going to look at both my athletics and my academics by combining them and viewing some of my favorite activities within sports through the lens of engineering. Alright, so we're going to look at hurdles first. And we're going to first look at, compared to my actual times that I run, we're going to try and see if we can use some math to find the fastest times I could hypothetically run. So we're going to start. My 100-meter time is 11.94, and my 110 hurdles time is 15.62 seconds. So if we convert my 100-meter time by multiplying by 1.1 into a 110-meter time, we can then subtract the difference in my 110 hurdles time with then my calculated 110-meter dash time to find the time added by the hurdles alone. So if we go up here, we can find my velocity by our velocity equation, distance over time, 100 meters, my 100-meter time. This is the speed I run. Now we're going to go down here and look at the hurdles race. So from the start line to the first hurdle, it is 13.72 meters. Between the hurdles, it is 9.41 meters. There are a total of 10 hurdles, so 9 times in between. And then between the last hurdle and the finish line is 14.02 meters. Now we go up here and we can use those things to calculate a hypothetical fastest time in the 110-meter hurdles. So we can take the distance to the first hurdle divided by the velocity, and then that will give us the time for that distance, t equals x over v, converted from our velocity equation. So distance divided by velocity to the first hurdle, plus the time added by each hurdle calculated earlier, plus then the distance between each hurdle divided by my velocity, multiplied by 9 times in between each of the hurdles, plus then the distance between the finish line and the last hurdle divided by my velocity. Added all those together, and we get 15.91 seconds as my hypothetical fastest 110-meter hurdle time. But now we have a problem. I actually run a 15.62, which is actually faster than 15.91. So we have to go back and look at something. However, I don't actually think it's my hurdles time that is incorrect. I think it's actually my 100-meter dash time that's incorrect, because I get to run the hurdles every week, and so I'm pretty consistent. I have a lot more data to show of, yes, I'm this fast. Versus I only run the 100 meters once or twice a season because of the way the events are scheduled and the other events I do. As such, we can use a simple proportion of my hypothetical 110 hurdles over my actual should equal then the actual 100-meter time over my actual 100-meter time. And we can use that proportion to solve and find that my hypothetical 100-meter time is actually 11.72 seconds, and that I run faster than 11.94. Alright, now we're we're going to look at soccer and me shooting a penalty kick. And we are going to try and figure out how athletic the goalie needs to be to save my penalty kick. So, the penalty kick distance is 11 meters. Humans can react in about 0.17 seconds. And after analyzing the video, my shot took half of a second to get to the goal. If we go to a schematic of the goal, if it's 11 meters to it, I'm pretty accurate. I'm aiming for the upper corner, and we're going to say that I was about half a meter in from the post and half a meter down from the crossbar. So, right there. It's 11 meters to the goal, and then over 3.16. Then we have a distance along the ground of 11.45 meters, and then we can use another triangle up here along the face of the goal. If it went up 1.94 meters from the center of the goal, it is 3.708 meters to the point where the ball reached the plane of the goal. And then we can use a third triangle in 3 dimensions here, and we can find that the ball traveled 11.608 meters to the plane of the goal. Now, if we go up here, my shot went 11.608 meters in half of a second, so I shoot the ball at 23-ish meters per second and around 56 miles an hour. Now, if we find the time that my shot took, minus our human reaction time, the goalie has about a third of a second to save the shot. Most goalies are pretty tall. You want them to be able to reach all the way to the top of the crossbar, and I am 6'3". Most goalies are around my height. I can reach straight up to 8 feet, or 2.44 meters, the height of the goal. So, if we take the distance from the center of the goal to where my shot entered the goal, subtracting then the reach of the goalie when he's fully extended, the goalie has to leap an additional 1.27 meters. We can use our velocity equation and find that he needed to leap at an initial velocity of 3.857 meters. Now we're going to use a projectile motion equation and find out exactly how athletic that goalie is and how high he would jump, what his vertical leap would be if he was able to push off with that amount of force at that speed. So, plugging everything in, we find that our goalie is able to jump 0.754 meters, or about 30 inches straight up. Alright, so now we're going to look at basketball, and we have just seen me dunk a basketball. So, we're going to use those mechanics to find out what my hypothetical leg press is using my vertical leap. So, my height is 6 feet 3 inches, or 1.905 meters. I can reach straight up to 8 feet, which is 2.44 meters. We know the hoop is 10 feet, or 3.048 meters. Now if we go over and look at the basketball, which has a radius of 11.9 centimeters, or a diameter of 0.2385 meters, we can say that when I dunk, I have to put about 2/3 of the ball over the rim, because an additional third is above my hands, in my hands. So, if we take the difference in my reach and the hoop, plus then 2/3 of the diameter of the ball, I must get 0.78686 meters off the ground to dunk a basketball, which is about 30.26 inches. Now, if we take my weight, which is 85.1 kilograms, convert that to newtons of 34.8, we can then use some energy equations, set my potential gravitational equal to my kinetic energy, and find the initial velocity that I jump off the ground with, being 3.883 meters per second. So if we look at then in a force diagram, I push off the ground, the force of the ground pushes up on me as I push back at it, as my normal force is much greater than my gravitational force, otherwise I would be staying on the ground. So if we go over here, we can use some projectile motion equations and plug in all of my initial velocity, the height I need to jump. We can solve for the acceleration, which incidentally happens to come out to be identical to acceleration due to gravity, just this time I'm accelerating upwards instead. So our sum of the forces equals mass times acceleration. Our normal force of the ground pushing on me as I push back on it, minus my gravitational force that we found over here, my weight in newtons, is then multiplied by my mass times the acceleration we just found, gives us the force that I push on the ground with when I jump being 1.669.54 newtons, or 374.43 pounds. Now, we're trying to find my hypothetical maximum leg press, assuming that the jump is the same motion is used in a leg press. However, a leg press machine is at about a 45-degree angle. It's at an angle versus I'm jumping straight up. So we can use a simple triangle here and some trigonometry. If I'm jumping straight up, we want to find the weight that I can push along that incline. So, using trigonometry, we find that my hypothetical maximum leg press is 529 pounds, 0.52. Alright, so lastly we're going to look at me doing a backflip into a pool, and we're going to use some math to see if I should ever attempt a backflip on the ground. So, if we start with my height of 6 feet 3 inches, then, or 1.905 meters, then if we say that because when I flip, my knees come to my chest, we can say that I'm about half my height at that point, so 0.9525 meters. Now, we're going to find my rotational force, my torque, tau, here, equals force times the radius times the sine of theta. So, our torque equals my force that I jump with, found from our basketball equation, times the angle I jump with, I'm just jumping straight up, times then my height. We find that I jump with a rotational force of 1,590 Newton meters. Now, Newton meters is equivalent to joules, which is a unit of energy. So we can set that equal to our kinetic energy, or 1/2 mv squared, and find that my velocity as I rotate is 6.11 meters per second. Now, if we go over here to my rotation, if I have a radius, we say, of 0.9525 meters, we can find that the circumference, or the distance I have to travel, is 5.987 meters. We can use then a velocity equation and go here and substitute that to t equals distance divided by velocity. We can find my distance and my velocity, and so my rotational time is 0.98 seconds. Now, we go here and we will use our projectile motion equation, plug in our acceleration due to gravity and my initial velocity, found again from our basketball equation earlier, and we find that my air time when I jump, assuming that a basketball dunk is about my maximum vertical, I have an air time of 0.79 seconds, which, if you'll notice over here, 0.98 seconds is actually less or greater than 0.79 seconds. So, no backflips on the ground because it's going to take me longer to rotate than it is I'm going to spend in the air. However, let's now find how high I would have to jump to actually be able to backflip on the ground. So, if we go back to the same projectile motion equation, but now plug in the time and solve for the initial velocity, we find that I would need an initial velocity of 4.79 meters per second. Plugging that into another projectile motion equation, we can find that my height that I would jump to then is 1.167 meters, or 46 inches. In essence, I would need a 46-inch vertical to be able to complete a backflip on the ground with my current rotational force. So, I don't think I'll be trying that anytime soon without the safety of the pool.